Okay, so let's continue again, and I think we got disconnected in between. So I would continue from where we left. So I was saying like let's try listing some observation which would help to build our overall answer or observe or intuition ahead. So first observation is like if someone doesn't decorate, game ends there. Like if someone doesn't decorate, then no person ahead can decorate because it would be faltering the game because the question says that if someone doesn't decorate, then game should end, which means no more decoration should be left, which means all decorations are over. I 0, which means all decoration are 0. Okay, then if someone doesn't decorate, which means that after me, no decoration happens, which means after me no larger number can be there. Larger number can be there. Like if I am 3, then I can surely say that after me there can't be any 4 because I I can play game for 3 rounds, but he needs to play game for 4 rounds. How can this happen? Because I can play for 3 rounds, and when my round ends, the game ends. So how can he play for 4 rounds? Because like if it was 3-4, it would he decorates, then he decorates, then it would happen 1-2, then it would happen 0, then 1. Now is it's done, but he can't decorate because he has no decoration left. So this is wrong thing because there should not be an increasing part, which means that array should be decreasing. So I can write it like from 4 I can say array should be decreasing. What array are we talking about? We are considering array after borrowing. What's borrowing? Borrowing is equals to taking 0 box help, which means like what is borrowing? If I don't have my own thing, then I take someone else thing. So if I don't have my own decoration, I take zero box decoration, which is equals to borrowing. So we are considering array after borrowing. So array after borrowing should be decreasing. And what decreasing? As I said earlier, the difference of elements can't be greater than 1, which means the difference would be at max 1. Like this is a wrong array because 5-3 is wrong because 5-3, what would happen in 5-3? I decorate, he decorates, I decorate, he decorates, I decorate, he decorates. Now I decorate, then he has no option to decorate because he don't have any array left. Now after that there is still my one decoration left and the game is gone because game is wrong because I can't decorate and there is still one decoration left. So this is violation of rule 1. If someone doesn't decorate, game ends there, which means all decorations are 0. But no all decorations are 0 because this is one decoration left. So difference between the elements can't be greater than 1. So what from mainly these 2 points, from mainly I can say from fourth and from sixth, what I can say that array is decreasing and array the difference should not be greater than 1, which means that array would look something like x, 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 x and x minus 1, x minus 1, x minus 1 and bus itna hi. The array would be have some elements same, then some elements maximum minus 1, like this only. So if I take one example from the input, like this was the input. Okay, so this is the input. Now this is box 0. This is box 0. This is box 1, 2, 3. Okay. So first of all, as I said, the array should be the difference should be 1. Should be at max 1, which means that this is wrong because difference of 2 and 0 is 2. This can't happen. So this 0 needs to be converted to 1, which means I need to borrow one thing from here. Now it would be converted to 2, 1 1 because I borrowed 1 from here, and box 0 is 0. Now from 1 it became 0. Now is this array good? Yes, this array is good because this looks something like x, x minus 1, x minus 1. How is this good? How would game happen? I decorate, he decorates, he decorates. It game converts to 1 0 0. Then I decorate at last 0 0 0 and I stop the game. And if I stop the game is over and no one else decorates and it is good. So 2 1 1 is good. So how many permutation of 2 1? If this permutation I can swap these two, and this it would still go 2 1 1. Like if it was 2 0 1 and I borrow here, then this is also a good permutation because 2 1 1 is still good. So these are two permutation I can get. So what I can say that at last there would be some x's and some x minus 1. So if I can get the fixed count of x and if I can get the fixed count of x minus 1, then answer would be like if this is n1 and if this is n2, the answer at last would be n1 factorial into n2 factorial. Like here it was 2 and 1, like here it was 1 and these are two elements. So 1 factorial into 2 factorial, which is equals to 2, and the final answer is 2 here. Similarly, let's try for this as well. Hmm. So this is box 0 and this is box 1, 2, 3, 4. So first of all, first thing first, let's make the array decreasing at first. 4, 2, 1, 1. Now the difference can't be greater than 1, which means that these two elements should be 3. At least 3, these three elements should be at least 3. So let's convert them to 3 first. So converting them 3 would require plus 1 here, which is 3, plus 2 plus 2. So 3 3. And how many elements are left? 6. There were total 6 and we have used 5. So there is 1 left, which means 1 is left, and the array is looking something like 4 3 3 3. Now there is 1. So can I add here 1? Can I add 1 here? No. Why? Because this would be wrong because it would become 4 3 4 3, and our one of the rules was that array should be decreasing, which would be violated. The fourth rule, array should be decreasing. So this rule is violated. So we need to add here only. So 4 4 3 3. Now how many arrays of 4 4 3 3 can I make? So first of all, how many arrangements? What are the arrangements here? For 4 4 3 3, 2 factorial arrangements here, 2 factorial arrangement here, which makes it 4. Now we were having three choices of making 4. Like these were three choices. So total three choices we have, and how many 4s do I need to make? I need to make only one 4. So 3C1. I can either make this and bring it to front. I can either make this and bring it to front. Like 4 3 3 3. So I can bring it to front and it would become 4 4 3 3. So this makes it finally 3C1, which means total choices into how many zeros, how many zero decorations we have left, into 2 factorial into 2 factorial. Okay, done. So what would happen if we have lot of decorations left? Like here it was 3C1. Let's say I was having 10 decorations left. So I can say that I can any permutation is good because after if I have after make I have, if I have made this, now I have enough decorations left to cover any of this, like 3 4 3 3. I can still cover this. How? Because I have enough decorations left. I can make it to 4. I can make it to 4. I can make it to 4. So 4, 4, 4, 4. And I have still decoration left. And whatever decorations are left, people would be taking from the zero decoration box. And after they are taking from zero decoration box, I still have enough decorations left. So got it? So if I have, if this is greater than this, like if 3C1, like if 3C, if there is xcy, and if y is greater than x, then I can surely say that answer would be n factorial because I have enough decorations left. So let's look into the code here. So this is just a template for NCR and modular arithmetic and factorials. And now what I do is I first of all take input. So I take only n elements input and I mark the zeroth element separately in the zero number in the element name 0, and I now sort them in increasing order, and the maximum element is a dot back. So first of all I try to see that can I make all of them equals to maximum, like the if the array was 4 4 3 2, so can I make all of them to 4, this to 4, this to 4. So if I can do this, so how many operations are I require is difference of the maximum minus ai. If these are the operations required, so can I do this? If I can do this, so if these are total operations required and I can do this, so answer would be n factorial, because I have enough operations left. I have enough zero decorations that I can make any permutation good. So this is n factorial, like we discussed. This was the last case. And what else? So now I try to make all of them to max minus 1, because at least they should be max minus 1. So if any element is already max, so I don't need to make to max minus 1, because it would be, we can't reduce anything, we can increase only, we can borrow only. So I try to make the element to max minus 1, and these are the total. I reset diff to 0, and I see how many operations do I require. So if difference are already like I need 5 operation to make all elements to max minus 1, and I only have 3k, I only have 3 0 0, like I can only borrow 3, so this is already wrong. So in this case answer would be 0. So this is the base case. And now how many elements would be max minus 1? So I traverse and check how many elements are max minus 1, like I convert max minus 1 here, and I see how many max minus 1 are there. So at last, how what would be our answer? X C Y. What is x and what is y? X is total number of maximum elements, uh, like let's see 0. So what is less and what is 0? So uh, what is less? Less is how many elements are equals to max minus 1. So like in this case 4 3 3 3. So this is less, like 3 elements are ready to be becoming 4. So these are 3 elements. How and how many choices of 4 we can make? Like this was how many zeros operations we have left. So this here was 3C1. So like similarly, how many smaller elements we have and how many can we convert to bigger? So how many choices do we have? Smaller can be put into bigger basket. So 3C1 or XCY or less C0, and rest is the how many total big elements are made and how many total elements are made and their factorial, n1 factorial into n2 factorial. So similarly, less, so all less are converted to 0. So total there are max elements, and total there are less elements. So these are some max element basket and these are some less element basket, and some of them, and how many sum of them? Zero number of them would be changed to max. So total how many would be left? N minus less plus 0, and how many are this would remain. So if I put this to this, so this would become less minus 0, and if this is this, so this would be total minus less minus 0. So these two factorial. So this into, I multiply this fact 1 into fact 2 into fact 3, and this would be our final answer. Okay, so I hope this is clear. Now let's move to the fourth question. Fifth question, I sorry. So this is New Year gift. So this was, I think, the easier one than the D problem. The D problem was a bit complicated, or formula wise it was easy, but the thinking wise it was a bit difficult. But E problem was, I can say it was fairly simple or quicker to get. So what does it say? That we have we need to make, we have n friends and m boxes to place gifts in it. So we have to make some gifts and we have to give each of our friends. Each of our n friends should get at least one gift. Would get one way, not at least, would get exactly one gift, and they but they would not be happy in any gift they want. In any gift they get, they would only be happy in one of the following condition. What are these two condition? Either either the box is at least of beauty xi, or either the gift is at least worth zi. What does it mean? That either we spend zi rupees on their gift, or we wrap their gift in xith box. So what are both of the limitation? we have fixed money, and we have fixed number of boxes. So like we can use only one box size. So these are the two limitations. So we can't make every one of them happy in any case, in every case. So we need to figure out maximum number of friends we can make them happy. So we have total k coins. So what are nmk? N is total friends, n is boxes, and k is money, coins, let's say. So I need to make them happy, and the input is something like array of m elements, which are these are the boxes, and these are the constraint on the friends x, y, and z. Okay, so let's write it down here. So boxes are a1, a2, a3, and am, and friends are xi, yi, and zi, and these are n inputs. Okay. So first of all, okay, one condition we missed reading is Monocore wants to give worth at least yi coins to ith friend. So each friend get one gift, but he won't be happy in the gift he gets. He won't only be happy in these two cases. So, but still he needs to give yi coins to all of them. So, can I say that sum of yi should be at least smaller than k? This should be the problem constraint, and this is already given. Sum of yi, sum of gifts, sum of base gifts is already we have already that much money with us. So y1, y2, y3, and so on. So this sum should be at least k. Okay. Hmm. So if we are this, so what additional can we do to make them happy? So either we take xith box, or we spend if I write it clearly here, let's say not this, to make happy, what do we need to do? First choice is take at least box of beauty. So these are beauties of boxes. Box is beauty of beauty xi. Or second thing, at least spend zi minus yi more money. What's this? So we have already spent yi money on their gift, but they would be happy if we spend zi money on that. So to make them happy, we need to spend what more? Like if we have spent 3 rupees on them, but they would be happy if we spend 5 rupees on them. So how much more rupees do we spend on them? 2 more rupees. So these are the two constraints. So first of all, the money is fixed. So let's try to see whichever friends we can make happy with the boxes thing. Like if we are able to make someone happy with the box, then why should I spend money? Because box are free, but just they are limited. So if I can make a friend happy with box, so I would try to make them happy with a box only, not by spending more money. So if we can make happy with box, then why spend money? But problem here is like why spend money? But problem is what is a greedy choice here? So greedy choice is, let's say two people are there, two people. One first person requires 100 more money, and or or a box thing. Or second person requires 10 more money, or a boxing from the box I mean, or a beautiful box. Let's write it like this. Beautiful box, or here. So what would you try to do here? So first of all, I was saying, like, let's try with making them happy with the box only. So whom would you try to make happy with the box first? This one or this one? I would say this one, because if I try to spend more money on him, he would take 100 money. But he would but so I can, like, अगर मैं बोलूँ कि या इसको 100 रुपए ज्यादा चाहिए, पर ये बॉक्स से भी खुश हो जाएगा, पर एक बंदे को 10 रुपए ज्यादा चाहिए पर वो बॉक्स से खुश होगा। तो अच्छा तो यही है ना कि 100 रुपए वाले को पैसे की जगह बॉक्स ही दे दो। अगर वो बॉक्स से खुश हो जाए तो मेरे 100 रुपए बच जाएंगे। पर अगर दूसरे केस में मेरे तो सिर्फ 10 रुपए बचेंगे, तो मैं ट्राई करूंगा कि आई वुड ट्राई कि जो ज्यादा पैसे ले रहा है, जो ज्यादा पैसे की डिमांड कर रहा है, उसको मैं बॉक्स से खुश कर दूं। ओके। तो व्हाट्स ग्रीडी चॉइस हियर? ग्रीडी चॉइस, what's greedy choice here? Try to make more demanding person happy with box first। कि जो ज्यादा मतलब पैसे मांग रहा है उसको पहले बॉक्स से ही ट्राई कर लो, नहीं तो हमारे पैसे ज्यादा बच जाएंगे और मैं किसी दूसरे पर्सन पे खर्च कर पाऊंगा कि वो पैसे से खुश कर दो उसे। ओके, so this is the greedy choice. So what's the greedy then what to do? Sort people in order of their demand money। कि मतलब डिमांड मनी इज व्हाट इज डिमांड मनी? वाई आई माइनस एक्स आई। तो डिमांड मनी के बेसिस पे सॉर्ट करो। अगर कोई पर्सन 100 रुपए डिमांड कर रहा है और कोई पर्सन 10 रुपए डिमांड कर रहा है, तो पहले तो 100 रुपए वाले की बात सुनो, उसको बॉक्स से निपटाने की कोशिश करो। तो फॉर मेकिंग, ये बात हो रही है फॉर मेकिंग हैप्पी विद बॉक्स, हम पहले बॉक्स का काम करेंगे। हम जिन जिन को बॉक्स दे सकते हैं, टू ऑल पीपल वी कैन गिव विद अ बॉक्स, आई वुड ट्राई टू गिव देम अ बॉक्स एंड among them I would try to give them 2% demanding more money। So or if same money, if same demand, अगर सेम डिमांड है, दोनों 100 डिमांड कर रहे हैं, तो आई वुड ट्राई टू स्मॉलर बॉक्स, मतलब जो छोटे बॉक्स से खुश हो जाएगा उससे मैं ट्राई करूंगा खुश करने की। ठीक है। तो सॉर्ट किस बेसिस पे करा? सॉर्ट ऑन ग्रेटर वाई आई माइनस एक्स आई फर्स्ट, पहले इसको डील करेंगे। एल्स स्मॉलर बॉक्स विच इज एक्स आई। यहाँ पे गलत लिख दिया था, इट वुड बी जेड आई माइनस वाई आई आई गेस। हाँ, दिस इज जेड आई माइनस वाई आई, यहाँ पे भी जेड आई माइनस वाई आई एंड यहाँ पे एक्स आई बॉक्स। तो अगर पहले इनको देख लिया, अब हो सकता है कोई लोगों के लिए बॉक्स अवेलेबल हो। यहाँ पे आई वोंट बी स्पेंडिंग मनी हेयर, मैं यहाँ पे पैसे खर्च नहीं करूंगा, मैंने पहले सॉर्ट कर दिया। तो ऐसे 5 लोग खड़े हैं लाइन में। ठीक है, दीज आर पीपल स्टैंडिंग, और यहाँ पे इनकी डिमांड डिक्रीजिंग है। मतलब इफ ही डिमांड्स 100 मनी, ही डिमांड्स लाइक 70 मनी, ही डिमांड्स 50 मनी, ही डिमांड 10 मनी एंड समथिंग लाइक दिस। बट ही कैन हैव वेरिंग बॉक्सेस, लाइक ही कैन हैव a box of and 10 size, he can have box of 50 size, he can demand box of 30 size, he can demand box of 10 size and so on. Like the box choices could be random but the demand is surely decreasing. And if the demands are decreasing, so I check if the array of ai, a1, a2 and am, does it have a box of 10 size. So if it has 10 size, so I extract the 10 size, so which is the upper bound, a lower bound of this, lower bound of 10 exists in the box array. I can take this and take that box out. And if there is a 50 box, I can take, and if there is no 30 box, so I would skip this and I would skip this. So like his demand got completed, his demand got completed. So we will save like 170 rupees, but his demand could not be completed. So I would try to satisfy him with money. So I would push it into a separate array like 50. Now I would try to push it in separate array like 10. So now let's say there was another people with 5 and his demand got completed. He was demanding a smaller box only of one size, so his demand also got completed. So there are two people left, 50 and 10. These two people are left, so I would try to satisfy with them money. So whom do I satisfy first, 50 first or 10 first? Obviously 10 first because he demands more money. So if I check with k, do I have 10 money left? Yes, so then I do k minus 10. Now I check 50. Do I have 50 money left? No. So I won't do k minus 50 and stop here. So how many people I made happy? 3 from the box part and 1 from the money part. So total 4 people I made happy. Something like this. So greedy choice is very simple. But it's more like hint when if the hint hits us or the choice, the the way do how do we need to operate itself, then the question becomes easy. So let's say this was the question n m k, and this is a array, and these are x, y, and z. So first of all, how many money? First of all, both of them require two money. So I would just do. And what are the extra demand they are having? He has extra demand of one, which is this is z minus y, and he has extra demand of five. So he has extra demand of five. He has extra demand of one. But the money we have left is only two because six minus four already is done because these two are already demanding four money. So we don't have any choice here. So now we have only two money left. So first of all, what I can do is he is demanding five money. He is demanding one money. So whom do I satisfy first? So I try to satisfy this with a box. So he demands a box of one size, and we have a box of one size. So I make him happy and gift him a box of one size. Okay, so he is now happy. Now I need to make him happy. So he demands a box of one size. But do we have a box of one size? No, because this is already over. So he doesn't have a box of one size. So can I make him happy with money? Yes. He demands extra. What extra money does he demand? One. And do we have extra money? One. Yes, we already have two extra money. So yes, then this two gets changed to one. And yes, this is also happy. So how many people do we have we made happy? We have made two people happy. Yes, we have made two people happy. So, repeating what's our strategy here? Strategy first, sort people on basis of greater demand and smaller box first. People who are having greater demand should come first, and if the demand is same, then people who are demanding smaller box should come like. And now, then try to find their respective boxes. What are their respective boxes? Upper bound of xi. And then if not satisfied, keep them among all not satisfied. Try to satisfy the smaller ones with money. We now iterate in the sorted order from smaller to lower and try to satisfy them with money. So we first of all satisfy with the box, then we satisfy with the money, and this is the right greedy choice. So how does the code look like? So code looks something like this. NMK is taken an input. We had a vector of m size, and we have maintained a multiset. Multiset is what is for multiset? For finding the lower bound, and I think I have written upper bound here. Yes, it should be lower bound. Lower bound. What is lower bound? Greater than equals to. So we try to find the lower bound, and for that we have maintained a multiset. So we iterate in the A array, take the input and insert them into a multiset. And after that I take x, y, z, and already I by default reduce k y from the k because this one is already requiring, like here also 622. So here it was 6, and the 2 was yi is already required. We need to give at least yi. So that money won't be used in future. So I reduce from the k, and now what this is my demand, and this is the box this is the box. So extra demand, and this is the box. So I sort them and by a custom comparator function. What is the comparator? If first of all, if the first item is not smaller, so which means what is the first item? First item is the demand. So more demand comes first. More demand comes first. Otherwise, the smaller box comes first. The more demand comes first and smaller demand. So this is the cost and this is the beauty. So if I can satisfy with the beauty or with the box first, I satisfy with the box. I find the lower bound, and if it is present in the array, I increase the count and I erase the lower bound. Otherwise, I push into the extra vector, which means that these are not satisfied ones. And if among all those not satisfied, I sort them first. So I need to satisfy, मतलब जो कम पैसे में satisfy हो पा रहे उन्हें satisfy करूंगा. So I sort them and I iterate them, and if they are greater than, if I can satisfy them, I reduce them and increase my count, and this is my final count. So the code is fairly simple. The idea was also, I guess, simpler than the D problem. So yes, this was it. We have discussed A, B, C, D, E problem, and if there is any doubt or problem or any more feedback on my explanation, do let me know in the comments. Thank you.